Hello everyone. Today we are going to discuss about one of the most popular cryptographic algorithms, the data encryption standard. We will see how the encryption and decryption in DES works. Before we start with the encryption process, we need to know about certain things. Firstly, DES is a block cipher. That is, it works with a certain number of bits at a time, and this bit block size is of 64 bits. DES is a private key algorithm and the size of the key is 64 bits. Next, the input to the encryption process is a 64-bit plain text and the output is also a 64-bit block, and we call it a 64-bit ciphertext. Here, plain text is simply the representation of the text message in terms of bits. So as shown, if we want to represent capital H in terms of plain text, we consider the ASCII value of capital H, which is 72, convert it into a hexadecimal equivalent, which is 48, and then represent each digit of the hexadecimal into a 4-bit binary equivalent. So 4 is represented by 0100, 8 is represented by 1000. So likewise, H is represented, and so likewise each alphabet and each symbol can be represented in plain text. So the first step in encryption process is initial permutation, which is just a basic rearrangement of bits. Now if we imagine the 64-bit plain text in a table of 8 cross 8, we get the table on the left hand side where the numbers represent the respective bit positions. After passing it through the initial permutation block, what we get is the table on the right hand side. So here, as we can see on the right hand side, the first bit is replaced by the 58th bit, the second bit is replaced by the 50th bit, and so on. So as we can see, this is just a basic rearrangement of bits. Next, we send the output from the IP block to the most important part of the algorithm, the round function. As we can see, there are total 16 rounds, each giving an output of 64 bits. But we also see that the input to the round function is not only the 64 bits from the plain text side, but also a subkey, and this is from the private key. So for each round, there is a unique subkey. So in all, there are total 16 subkeys, each of size 48 bits, and all are generated from the 64-bit private key. So how are these subkeys generated? In the original 64-bit private key, there are 8 parity bits, and every 8th bit is a parity bit. So bit number 8, bit number 16, and so on are parity bits. These bits are not used further and are simply removed. Now, the remaining 56 bits are divided into two parts, each of 28 bits. And this entire thing is done by the permuted choice 1 block, the PC1 block. Now, within each of these two blocks, we perform a left circular shift, and by how many places these left shifts have to be done depend on the round number. So, for round number 1, 2, 9, 16, we perform left shift by one place, and for the rest, left shift is done by two places. Now, these blocks C1 and D1 obtained from left shift are combined again to form a 56-bit block, and then this block undergoes a compression permutation under the name PC2. This is called compression permutation, as what it does basically is discard some bits and rearranges the remaining ones. So we send 56 bits and we get 48 bits as output. Now our first subkey of 48 bits is ready. For the next subkey, the blocks C1 and D1 serve as inputs, and like this the entire process is repeated. So this way all the 16 subkeys are generated. Now that we have seen the subkey generation, let us look what the round function does. So firstly, in the round function, we are taking the 64-bit block input from the plain text side, dividing it into two 32-bit blocks left and right. Most of our operations are performed on the right block. An expansion permutation is performed on the right block where some of the bits are duplicated and rearranged, and so due to this the input is of 32 bits and the output is of 48 bits. These 48 bits and the 48 bits of the subkey are undergoing a XOR operation. The bits obtained after XOR operation are sent to the substitution boxes. The input to this block is of 48 bits and the output is 32 bits. So there are total 8 S boxes or substitution boxes. In total, one box is for 6 bits each. S box is basically a table with 4 rows R0, R1, R2, R3 and 16 columns C0, C1, C2 till C15. So for one S box there are 6 bits as input, and out of these bits the first and the last bit represent the the row number of the S box, and the remaining 4 bits represent the column number of the S box. This gives us access to one cell of the S box. The number stored at this cell is converted to a 4-bit binary equivalent, which is the output of the S box. So like this, from 8 S boxes we get 4 into 8, that is equal to 32 bits. These 32 bits are rearranged in permutation block, and then these bits and the left block bits are undergoing a XOR operation again to give us the final 32-bit right block. The initial right block simply serves as the final left block. Hence, the output is of 64 bits. The entire process is repeated for all 16 rounds, and at the end of the 16th round, the final left and right blocks are swapped. Now, the final step to obtain the ciphertext is inverse permutation, where the bits are rearranged for the last time to give the required 64-bit ciphertext. So, the entire encryption process can be summarized by this block diagram. The decryption is nothing but just a copy of the encryption process, and the only difference we see here is that the subkeys are used in the reverse order. A more secure algorithm is the triple DES, where we use 3 keys instead of 1, but we still use the DES algorithm to do encryption and decryption. So, encryption in DES is as follows. We first encrypt the plain text with the key K1, decrypt the output of the encryption with K2, and encrypt it with K3 to obtain the ciphertext. Decryption is exactly the opposite. We decrypt the ciphertext with K3 first, encrypt it with K2, and decrypt it with K1 to obtain the plain text. So as we see, TDS offers triple layer security to enable better reliability.